Let's start now. I guess this will be the audience and the players online. Welcome back to the second session of HOPE here. I hope you had a good break. We'll kick this session off with Simon, and he'll go talk about event-driven multi-party session actors. Take it away.
Thank you very much for the introduction. So hello everyone. So today I'm going to be talking about some joint work with Ray Hu from Queen Mary about how we can use effect typing and event-driven programming to support session typing. So that's essentially typing for communication protocols for actor languages. So this is my first time talking at HOPE. I'm really excited to be here, so thank you for having me. And it's certainly more on the applied side. So this is really a talk about using HOPE concepts rather than inventing any new effects machinery. But I hope it'll be interesting to see how we can use some of the things from effect systems in order to address a pressing challenge, at least in the session typing community. Okay, so first, just to talk a bit about actor languages. So you might have heard of languages like Erlang, so there's the Erlang workshop today as well. Frameworks like Akka and languages like Elixir. So these are what's known as communication-centric programming languages. Communication-centric programming is essentially about communication and concurrency where we don't have any shared memory coordination, or at least not at the level that the programmer needs to worry about. Essentially what we have here are lightweight processes which communicate only using explicit message passing. And as a result, they've become quite popular for writing reliable distributed code. So the one big success story of Erlang, and I mean there are plenty, but one of the big ones is that it powers WhatsApp, which has actually more than 2 billion users, I found out this morning. And this is because it supports, the way that these processes are structured, the way that the language is designed, means that we can support data locality and idioms such as supervision hierarchies, which allow us to kind of restart things if things go wrong. So, I mean, it's a really good paradigm, but I mean, it's not panacea, right? So, as with any kind of concurrent language, we have things like communication mismatches. So this is when we receive a message that we're not expecting or receive a message which has a payload of the wrong type. We've got things like deadlocks, so cyclic dependencies, meaning that communication can't proceed. And nastier things like live locks, where we've got something happening, but it's starving out something else interesting happening in the system. So a particularly kind of busy area in this kind of space is multi-party session typing. So this started in about 2008. And the idea is that what we do is we give a type discipline to communication protocols. The idea is if we can then go and type according to a session type, then we can be sure that our programs actually follow the communication that we say they do, and we can rule out some communication errors statically. So in multi-party session typing, what we do is we specify all of the interactions as what's known as a global type. And then what we can do is we can project this global type at each of the different participants. So it's easy to write a global type. Then we can go and get the protocol from the point of view of each participant. And at that point, we can use those local types to do some enforcement of the communication behavior. So that might be static type checking. It might be dynamic monitoring, for example. So the kind of big canonical example, and most session typing people kind of roll their eyes when they see this, but it's short and it's neat, is what's known as the two-buyer protocol. So the idea here is that we have 3 participants. We've got a buyer, a seller, buyer 1, buyer 2, and a seller, and they need to coordinate to buy an expensive item, typically a textbook, and given the US textbook market. So the way that this proceeds is that buyer 1 asks for a quote from the seller, and then buyer 1 contacts buyer 2 with the share that they want buyer 2 to pay. And then it's up to buyer 2 to decide and communicate with the seller whether they want to go and accept that or not. So we can write this down very succinctly using a global type over here. So we have this kind of Alice to Bob notation. So we say, right, so buyer 1 is going to go and send a message to the seller with a label title and a payload string. And then the seller's going to go and communicate with the buyer 1, sending back the quote and so on. And at the point where we go and communicate with the buyer 2 and the seller, there's 2 different branches that we can potentially take. So we're allowed to make choices in this as well. Laser pointer, okay. Oh, nice. Thank you. Okay, so from that, what we can do is we can do the projection. So now what we've got up here is, well, if we project at buyer 1, we look at all of the different interactions that buyer 1 has, and then just go and just take those, right? So the first thing that we need to do is go and send a message to the seller. So there we see that kind of O+ notation, which means send. And then at the seller, we need to go and receive using that kind of ampersand notation, and so on. So at this point, we don't have irrelevant interactions, and we can just type check the behavior just according to that kind of fragment of the protocol. And it's the same for buyer 2 and the seller as well. Okay, so the first question is, well, we've got session typing, and it's been, it's been a busy field, but how can we apply session types to actor languages? And the idea, it's not actually as straightforward as you might think. And this is because of the underlying kind of model of the communication-centric language. So session types were originally thought about in the context of the pi calculus, which is a model for channel-based communication. And what we have here are kind of named buffers or endpoints, which are shared between anonymous processes. So each process can have access to many channels at a time. And these are very easy to type, right? So we can, in Go, we can have channels over which you can send and receive integers. And that's just completely native to the design. The problem is, a lot of the time, distributed programming with channels can be difficult. So the moment that you want to go and send channel endpoints over other channels, for example, which is a really important pattern, the distribution story gets a bit hazy. Similarly, when we've got things like choosing about which channel we want to receive on, again, that's the sort of thing that typically requires a distributed algorithm. But on the other hand, we can give them quite descriptive types. So these are binary session types here, so just between 2 participants. But at the top we can say, well, I'm going to receive 2 integers and send a bool. And then we can type check the dual of this, so the other end of the channel, with send 2 integers and receive a bool, and so on. Now, actually doing this for actors is slightly trickier, right? And that's because the model that actors use are having a single incoming message queue associated with each named process. Now, this is way more easy to distribute, but way more difficult to type. So whereas here we can have this kind of bidirectional sort of sending and receiving, these are all receive only. So there are 2 kind of main approaches that we can use to get some sort of behavioral type discipline for actor systems. The first is assign a type to the mailbox. Now, you can't do this with session types. You need a separate type of behavioral type system for this, and I'm going to be talking about this at ICFP tomorrow. But if we actually want session typing, where we talk about the communication protocols, really what we need to do is we need to use the session types to govern the actions that we can perform. And this is essentially the approach that I'm going to be talking about today. So, back in 2014, there was the first big work on actually using session types for actor systems. So this is due to Raymond and Elixir and Nobuko Yoshida. And the idea here is that each actor can take part in multiple roles in multiple sessions. And there's a really big benefit to this in that, because you're taking kind of identity of processes really seriously, you can share state between the different sessions quite easily. Now, this work used runtime monitoring to check against session types. So there was no static type checking here, and there was no kind of underlying formalism to it either. But I mean, it was very useful because it was the first time that we really saw how we might design a session typing discipline for actor languages. So some work that my colleagues from Glasgow and I did in 2021, which we presented at eCoop, essentially used a flow-sensitive effect typing judgment to enforce session typing. So and this was used quite early on when people were talking about language implementations of session types in the binary world. But it actually works really well for actor systems when we want to do static typing. And the idea here is we've got this typing judgment which says under type environment M and precondition S, which will be a session type, term M has got type A and advances that session type to some T. So this worked really nicely, and we managed to get some really nice guarantees about dynamic behavior. So finding other actors, replacing, dynamic replacement of behaviors. But there was a big limitation, and that's that we could only type things using one session at a time, which kind of deprived us of one of the big benefits of being able to have that shared state between different sessions. So this is the state of the art at the moment, where we can choose either have dynamic checking and multiple sessions, or static checking and a single session. And the purpose of this work is to get the best of both worlds. So we want static checking and multiple sessions. And the key idea that we've come up with our programming model that I'm presenting today is to combine the flow-sensitive effect system with the paradigm of event-driven programming and first-class event handlers. So just a refresher on event-driven programming. Essentially what we have is we have a process which performs an event loop. It's idle until it gets an incoming event. When it gets an incoming event, it will invoke an event handler, and the event handler can perform some computation, perform some side effects, and after that it will go back to being idle again until you get the next event. So there are kind of four main components to our model. The first is, of course, isolated processes. We don't want things like shared memory, at least to be used by the user. The second is to have first-class event handlers, right? So what we want is values which can tell us how to react when we get an incoming message. And this actually gets quite powerful because what we can start doing then is passing these event handlers around and actually allow dynamic communication of how to behave based on various computation. The next thing is we're sticking with a flow-sensitive effect typing discipline. So we want to actually just talk about the actions that we're allowed to perform rather than talking about the mailbox itself. And finally is a way of establishing sessions. So there's a lot of work in session typing using something known as access points, which act as a kind of matchmaking abstraction where people register to take part in something and then a session becomes established. And we have generalized that from binary session types to multi-party session types. Okay, so just to give you an idea of how this all works out. So here is the main process which sets everything up. And the idea is we begin by creating a new access point which allows the two-buyer session to be established. So we annotate this with the different roles and the different local types that can take part in this session. Next, what we do is we spawn the seller, and we spawn two sets of buyers as well. And we give these all that access point name, so they can all kind of set themselves up in order to communicate. Now, importantly, this is, so there's only one seller, but it can take part in multiple sessions. So, we don't restrict ourselves to just talking to one person at a time. Now, how is the seller implemented? So essentially, the first thing that we need to do is to register to take part in one of these sessions on this access point here. So register takes 3 parameters. It takes the access point that we want to register on, the role that we want to play, and a callback to be invoked whenever a session is set up. So what this will do is it will recursively register, and then it will suspend waiting for a title message. So a title handler, and I'm using the word handler here just to stress this is not an effect handler, this is an event handler. What this will do is it says, right, well, I'm going to handle a message from buyer 1, and I'll handle the title message, at which point I will send a quote, and then I'll suspend awaiting a decision. And finally, we have the decision handler down here, and this is invoked when the decision has been received from buyer 2, it sends the date to buyer 2, or it terminates. So you'll notice down here we don't need to suspend again, because we've actually completed everything that we said that we were going to complete, and we don't need to do anything further. Okay, so onto the kind of formal part. What we have is a small core calculus, which is built on fine-grained call by value. So what we have is an explicit stratification between values and computations. Our values are variables, functions, recursive functions, constants, and these handlers. And our computations involve sequencing, and return allows us to go and treat a value as a computation, function application, conditionals, and then this merry band that I'll talk about in detail when I show you the typing rules. But as you see, let is the only evaluation context that we have. So we explicitly sequence all of the computations, and this makes typing quite a lot cleaner. So as you might expect, we've got two typing judgments. So the first one is the standard value typing judgment, saying that we've value under environment gamma, value v has got type A. And the second is this flow-sensitive judgment that I showed you earlier, which says under environment gamma with precondition, session precondition S, computation M has got type A and postcondition T. So we can see now how this actually gels with the session typing. So what we're trying to do here is we are trying to send something to role P, so send a message with label LJ, payload V to role P, right? Now, what we're saying is this is only valid if we've got a session type, a send session type precondition here, and we've got that LJ is supported by that session type, and the payload of the value is matched to what we've got in the session precondition. Now, this is a completely side-effecting operation, so we return the unit type, and based on which label we have there, we update the postcondition to the continuation of that particular branch that we've chosen. Now, here is the handler judgment. So what we have here is, well, we want to go and type a handler, and it's parameterized by a receive session type. So we want to go and receive from role P, and we've got branches Li, Ai, Si. And essentially for each of these, what we want to do is, well, we want to extend the context with what we've received. We want to go and type each continuation with the continuation of the session type. And for each of these things, we want the entire term to return the unit type and have used up all of its session contents. So we can do that in two ways. We can either complete all of the remaining interactions in that session, or we can suspend and then we'll go back to idle. Now, suspending works by saying, right, so I want to go and suspend. I need to go and provide a handler whose type parameter matches with our current session precondition. And this is a bit like raising an exception. So you don't return back into the evaluation context that you come from. So you can have an arbitrary return type and an arbitrary postcondition. What spawn does is it allows us to create a new process, and whenever we spawn something off, it's not in a session by default. That's the point that that can register to take part in another session. And finally, the two last rules are for creating access points and registering on access points. And essentially what we do is whenever we want to go and create a new access point, we annotate it with the roles and local types. And these need to satisfy some customizable safety property. So we can tweak this phi to whatever we like. We can make it deadlock-free. We can make it live lock-free and so on. But it has to be what's known as safe, which is the minimum requirement for actually getting type preservation. And this means that we can't exchange values of mismatching types. Finally, registering takes an access point V, and the thing that we need to go and register on must be supported by that access point, and the continuation M must be typable under that particular local type. So we've got an operational semantics as well. I'm not going to go into details here, but at a high level, we represent each actor as a three-tuple, where T represents the process state. We can either be idle, we can either be evaluating M not in the context of a session, or evaluating M where we're playing role P in session S. We've got an environment which stores handlers, which are invoked whenever a message arrives. And finally, we've got initialization state, which is used to establish sessions. So this is going to go and contain our initialization callbacks. We formulate the semantics as a concurrent lambda calculus. So we've got a deterministic reduction on terms and a non-deterministic reduction on processes. And we've got an asynchronous communication model. So the meta theory is a work in progress, but we've got high hopes for it. So currently we've got that reduction preserves typability, and as a corollary, we've got that communication follows session types. In future, we're working on getting progress, a progress theorem, which says that either the system can take a step or every process is terminated. Fidelity, which says that if the session types can take a step, then that can be reflected in the processes. And also a global progress theorem, which says that if we don't have any unguarded recursion, every session in this system must be able to reduce. So at present, we've got syntax reduction rules and a type system, a preservation proof, and we've also got some implementations. So Ray in particular has implemented a type checker and a small step interpreter. And in future, as I say, we're going to really hammer on the meta theory. We want the ability to switch between sessions which are in a send state, which is slightly trickier. At the moment, the only way that we can switch between sessions is if we've suspended and we get a message coming in. And finally, we want to look at mainstream language implementation. So we've started doing some work on implementing this in Scala using API generation. Okay, so to sum up, actor languages are popular for writing reliable distributed code, but on their own, they can't rule out a class of communication errors. This is where session types come in, but they are difficult to apply to actors directly. So this work, this ongoing work, is the first statically checked application of session types to actor languages, where actors can take part in multiple sessions. And in order to accomplish this, we're using flow-sensitive effect typing and first-class event handlers. And it seems to work well so far. So yeah, I think that's everything. Thank you very much for your attention. I'd love to take any questions that you have.
All right, we have a question right here. I'll go to Ohad.
Thanks for the talk. You keep saying event handlers are not effect handlers. So what's the evidence? And also maybe a bit less trolling, sorry. What would you need to add to effect handlers so that you could actually implement, maybe not event handlers, but schedulers with event handlers?
Okay, so I didn't want to make the claim that event handlers in general are not encodable by effect handlers. That's certainly not an argument I wanted to make. All I wanted to make sure was, given the expertise of this particular audience, I wanted to distinguish the terminology I was using from what people might automatically go to when they were thinking of handlers. I am almost certain that you can probably do some form of event handlers using effect handlers, certainly. Sorry, what was the other part of your question?
I guess So you're an expert on event handlers, right? So something is probably missing to make it convenient to implement event handlers with the effect handlers. What would be the kind of the crucial ingredients that you don't really see obviously with effect handlers?
I would have to think about it. One immediate thing that springs to mind is that effect handlers tend to be computations, whereas our event handlers are very much values. I'm sure you could work this out by funking things potentially, but that's, yeah. But good question, thank you.
I just have a question. Is this a continuation of this question, either of you? All right, okay, so we'll continue the order.
So yeah, I was going to ask if you'd compared what you're doing with the work on asynchronous effects by Mattia Pretner and Daniel Aumann, which I think does in some ways illuminate Ohad's question.
Mm-hmm.
So they're kind of, what's the word? There's a sort of duality between the kind of constructs that they consider and effect handlers.
Yep.
But yeah, have you thought about that?
I have not thought about it. I've got a lot of respect for that work. It's really, I remember seeing a talk on it and being very enthusiastic about it. I've not done a formal comparison yet, but I'll definitely look at it. Thank you.
Hi, thanks. So first off, a small continuation of the previous question. Yeah, you can implement scheduler with effect handlers, and that's pretty obvious. And actually, we recently made a small paper where we compile an actor language to concurrent lambda calculus and prove the simulation. So that works fine.
Okay. Yeah.
My question is a bit separate. Can you show back where you use the introduction of access point?
Yep.
First. So, well, the programming version.
Okay. Here, probably.
Yeah. So one thing that I found a little bit weird is that it seems like the contract you give to the access points is declared separately from the actor here.
Yeah.
And from a programming point of view, that seems very weird because the actor already sort of embed what you should communicate with it in its programming. Do you have do you have a better version, or do you expect to have some sort of inference? What do you expect from that point?
So the question, if I understand it, is where do you declare what a session is?
Sort of, yes. The typing.
Yeah. Okay. So when you register, you need to go and make sure that you actually provide something that actually abides by this session. It would be very difficult from a session typing point of view to declare things such that you would. Because I mean, when you're implementing an actor which goes and takes part in the session type, you're implementing the functionality which fulfills one role in that session type. And all of those roles have to work together, right? And you need some way of tying all of that together, and it would be very, very difficult, I think, to do that without giving the burden on, where you actually establish that session, essentially. But it's an interesting point. If you'd like to have a chat about it properly, that would be good. Just to actually continue on the effect handlers point, there's an argument I should have made, which is I didn't want to go and bring in all of the machinery of, effect handlers. I mean, the point, I wanted to go and get the smallest calculus that I could, and actually bringing in the entirety of effect handlers would be a bad idea. But I'm certainly not making any claims about generality.
All right, any further questions? Anything else? Yes, Max, right up here.
We have a question from the Discord, so maybe you should probably go in and answer it on Discord as well. But
yeah, I will.
The question is from Edwin Torok. They ask, where can they learn more about the monitoring approach that you mentioned in the beginning?
Right, okay. So essentially, local types, you can... so there's quite a rich body of work showing that local types can be represented as finite state machines, and there are plenty of pieces of work which do this translation quite efficiently as well. The point is that they're essentially regular languages. And what you can do, certainly with the actor version of things, is if you can set up all of these finite state machines, then dispatch these messages to these monitors. If you can make a transition from the state that you're currently in based on the message that you've just received, then you can advance the monitor and then pass that to the user process. If you can't make that transition, then you've got a violation and you need to flag that.
Thank you.
Thanks.
All right, any further questions? Otherwise, I have a little question. So I happen to know that you're sort of a world expert on fault tolerance in the presence of session types and distributed programming. Have you thought about fault tolerance here in this setting?
So that's a very good question. So in the eCoupe, so it's actually slightly more difficult to do this with an effect system than it is when you've got actual first-class endpoints. The eCoupe work actually has some handling of exceptions. So if you make a communication action that fails due to the other participant being unavailable, then you can cancel what you're currently in, raise an exception, and go out. Doing this in an effect system rather than a kind of first-class endpoint system is trickier because you can only scope, or the typing only really works out in an easy way if you scope your exception handlers over a single communication action. So it's a bit more tricky, but we do this in the HOPE'21 paper just in order to go and handle exceptional situations. In terms of fault tolerance in general, rather than resilience to errors which then need to propagate, I've not thought about that in a huge amount of depth. I've not thought about, replication and so on.
Right. I have a sort of follow-up on that. You mentioned Erlang
Yes.
earlier. Very dynamic language, but let's suppose we had a type system for it.
Yep.
One key property of it, I believe it has hot code reloading.
Yep.
So you can swap out a function on the fly. You deploy new code and stuff like this.
Mm-hmm.
Have you thought about how you can fit this session typing into this scheme where you can actually update your code on the fly? Or?
Yeah, so this is a really interesting question. So actually in our eCoupe'21 paper, we do this. We can only swap out things which are exactly, where the logic changes, but the session type that logic fulfills the same sessions before to an order consistency. But yeah, this is a real strength of using this kind of actor-style communication in that you can do that and the typing does work out.
So one question right there is can you do that mid-session or do you have to reset the session state?
So the way that it worked in the eCoupe paper was, you had essentially a loop, and whenever that ended, you could you would restart with the new behavior. I've not really thought about how this would work in this particular setting, but I think given that we've got these pluggable event handlers, it might be somewhat more naturally.
Right. Okay. One last question for me. One thing I didn't really get was why first-class event handlers? Why first-classness? What's?
That's a very good question. I think, the main thing, the first thing is that the typing works out. So if you can have something where you can suspend on something, then you don't need all of the different exit points matching up.
Okay.
So the first classness of it, I think what is your question really? What would happen if you made handlers computations rather than values?
Yeah, make them second class. Why is there? What does it buy me? I just wonder if there's some relation maybe to. I have very limited knowledge, but about pi calculus. I don't know if it corresponds to something in higher order pi calculus that you can pass these around, like you can pass channel names around. I don't know. So I
think there are certainly parallels to a higher order pi calculus where you do have code mobility. Right. It's a very, very good question. But for me, I think it just worked better. I mean, it seemed powerful. It seemed, like the right way to do it. Having it as a computation didn't seem to buy me anything.
All right. Okay. Well, sorry for asking that question. Let's move on. Thanks, Simon.
Thanks, everyone.